Good afternoon, students. So, welcome to GATE training program. So, in this session, we are going to discuss about the theory of computation fundamentals. So, in this, the first topic is finite automata and regular expression. And this today we are going to discuss about introduction to regular expression, and then what is regular language, regular expression operators, and then the languages of regular expression, and then conversion of regular expression to finite automata and finite automata to regular expression conversion. So before entering into the subjects, we have to know some basic concepts. Okay, these are all the key terms, most frequently used terms in theory of computation. So the first one is alphabet. So alphabet is nothing but the finite set of input symbols. And then coming to the string, string is a finite sequence of input symbols chosen from some alphabet. And then language is nothing but the set of strings chosen from the alphabet. So these are all the examples. The first one, alphabet, which is used to, the sigma is used to represent the alphabet, equal to, within curly braces, you have to mention the alphabets. That is here 0, 1. And then string is nothing but the collection of alphabets over the alphabet 0, 1. So here 0 is the first string, and then 1 is the next string, 100, 001, 1001, etc. That is, we can take any combination of 0 and 1 while forming the string. And then coming to the second example, we are taking the alphabet A, B. So in this, we are forming the string A, B, and then A, B, B, A, B, B, C, etc. And then the next one, language is nothing but the collection of strings over the alphabet A, B, which is the language. So, which is represented by capital L, and then find L equal to, so here this is the example for language, L equal to W, where W containing palindrome strings over the alphabet A, B, so that the language consists of A, B, A. So palindrome means in reverse order also we have to get the same string A, B, A, and then A, B, A, comma, B, A, B, etc. Okay, these are all the basic concepts. There is some basic terminologies in theory of computation. That is, first you should know about alphabet, string, and then the language. So, and then coming to the finite automata. So this is nothing but the graphical representation of our machine. So see, first one is the finite automata for identifiers. So in this, identifier means which is nothing but the user defined variables in any programming language. It may be a variables or it may be a user defined function name, etc. Okay, that is the identifier. It should starts with the letter. Letter means A to Z. It starts with A to Z and then followed by any number of letters or digits. This is the basic rule for defining an identifier. For example, sum is an identifier means, so yes, sum 1 is the identifier means S is the letter followed by U and then the another U and then the last one M and then last one we have a digit 1. Okay, well, this is the identifier. So for this particular identifier, we need to draw the mathematical model, the graphical representation. So in this, we have a graph representation. Graph means it consists of number of vertices and then the edges. Okay, so in circle, no, which is used to represent the states, and then the arrow symbol, which is used to represent the transmission from one state to another state. So here 0 is the initial state, so that we have to represent the arrow followed by the circle, and then you have to give the state name. 0 and 1 are the state names here, and then the first transition from state 0 to 1 with the symbol letter. So letter is nothing but the alphabets from small a to capital small z, capital A to capital Z, and then followed by any number of letters and then followed by the digit. So this is the finite automata for defining an identifier in any programming languages. Likewise, we have the finite automata for numbers also. So in this, one arrow followed by circle which is used to represent the start state, and then followed by one arrow symbol which is nothing but the edges from one state to another state. So in this we have digit and then followed by n number of digits. So for this we are forming an internal loop, which means the start and then the end state, it should be the same state. We are forming the internal loop which is used to read n number of digits. Using the same edge, we can read n number of digits. So this is the finite automata for defining a numbers. And then coming to the next one. So here, is there any easier way to represent the finite automata? Yes, we have an easier way to represent the finite automata. So for this, we can use regular expressions. So regular expression means which is the mathematical or algebraic representation of finite automata using regular operators. So and then next one, regular languages. So regular language means which is the collection of regular expressions, and then the next one, strings generated by the regular expressions. So we have two kinds of representation here. First one, finite automata, which is the graphical representation, and then the second one is the regular expression, which is nothing but the mathematical representation. Okay, see, so this is the conversion, that is from finite automata you can write the regular expression, and then from regular expression you can draw the finite automata. Okay, well, so that the finite automata and the regular expressions are the equal. So see here we have one small diagram now. In this we have start state and then two different edges with the input symbol A and B. Either you can go with the start state to next state via A, and then the start state to the next state via the input symbol B. Okay, so this is the finite automata representation. So we can represent the same thing with the help of our regular expression. So here the regular expression is A plus B, so that the regular language L equal to either A or B. And then the regular expression construction. So see here, these are all the basic operators we are using in our regular expression. So the first operator is union, and then the second one is the concatenation, and then third one is the closure operator. So for union, we are using plus. The symbol plus is used for union operation in regular expression. Likewise, the dot operator is for concatenation, and then the star for closure operators. Okay. So in our regular expression, we are using only the three operators, that is union operator, which means plus, and then the concatenation operator dot, and then the closure operator star. So we have the operators precedence also here from high level to low level. Star has the higher priority than dot and plus. Likewise, dot has the higher priority than plus, and then plus is the lower priority. And then the next one, the regular expression. With from the regular expression we can form the regular language, that is L is nothing but the language of the particular regular expression here. Likewise, we can construct the regular expression from the given language also, that is we can construct the language from regular expression, and then we can form the regular expression from the given regular language. So L is nothing but the language here. So see here the language generated by the regular expression. The next topic is we are going to construct the language from the regular expression. So here capital R is nothing but the regular expression, and then L of R is the regular language, which is defined as follows. That is L of phi, which is nothing but the empty language, which is equivalent to phi. L of epsilon, epsilon is nothing but the null string, equal to, within braces you can represent the epsilon. And then next one, we have the alphabet sigma equal to, within curly braces we have a comma b. So here sigma is nothing but the alphabet. Okay, this particular symbol is used to represent the alphabet. And then the next one, we can form the languages from the regular expression. So for example, here our regular expression is A. So capital R is nothing but the regular expression, and then the regular expression equal to, it consists of only one symbol, capital small a. So in language also we have the single symbol. So within curly braces, that is L is the language of small a equal to, within curly braces you have to mention the language small a. And then the next one, if R equal to B. So here R is the regular expression which is equal to the small b, and then L of B equal to small b. So these are all the regular expressions from the language. And then next one, so here the combination of more than one regular expressions. So see here R and S are the regular expressions. Then the regular language L is defined as follows. So for example, here we are using the first operator of our regular expression, that is union. So for union we are using the operator plus. So the regular expression is R plus S. R is the first regular expression and then S is the second regular expression. Here we are going to perform the union operation on both the regular expressions R and S. Okay, so that the language L of R plus equal to L of R union L of S, which means all strings that are either in the regular expression or in the regular expression S. Okay, this is the as usual union operations we studied in mathematics now. So here we are using the same type of operation, union operation here. So coming to the concatenation, so concatenation of two languages. So here we have the same language R and same regular expression R dot capital S is also the regular expression. So here R dot S means we are going to concatenate two regular expressions, that is R dot S. So you can write it as RS. So L of, while forming the language, you have to mention the language L of R dot S equal to L of R dot L of S, which means all strings that are of the form xy, yes, that is x belongs to L of R and y belongs to L of S. That is the first symbol, no, which is from the regular expression R, and then the second symbol y, which is from the regular expression S. So here we are going to concatenate both the regular expression into a single regular expression, that is R dot S. So x dot y here we are getting. So while forming the language, you have to mention L of R dot L of S instead of L of R dot S. So now coming to the closure property, that is closure operator of the regular expression. Regular expression, that is R star. So star is the closure operator in our regular expression. So L of R star equal to L of R whole star. So both are the same. So totally we have three different operators in regular expression. That is first one union, second one concatenation, and then the third one is the closure operator. So these are all the examples, some of the examples. So see the first one, A plus B is the regular expression. So that the language L of A union L of B, which means A union B. So that the language consists of A comma B, regular language, or L is nothing but the regular language. Here we are taking the alphabet A, B, 0, 1. Okay, in our alphabet, it consists of 4 symbols A, B, 0, 1. So here the first regular expression is A plus B. So now coming to the second one, AB plus BC. AB plus BC. So here first you have to divide this into two parts, that is AB in the first part and then BC in the second part. Okay, so that you can write it as L of AB union L of BC, which tends to AB union BC. So in while forming the regular language, within curly braces you have to write AB comma BC. And then the third one, A plus B into C. Okay, so this can be written as L of A plus B dot L of C, which means A comma B dot C. So you have to combine both this into a single language, that is AC comma BC. So likewise, A of 0 plus 1 dot B, A into 0 plus 1 into B. So here L of A, that is the first regular expression, small a is the first regular expression. So you have to write L of A dot, the second one is the 0 plus 1. So you have to write L of 0 plus 1 dot, and then the third one is the small b. So for that you have to write L of small b. So finally you have to write the string, that is within curly braces you have to write a 0 a dot 0 comma 1 dot b. So you have to combine all those things into a single language, means a0b a1b. So this is the regular language for the given regular expression. And then the last one, a plus b into 0 plus 1. So the first one, first you have to divide this into a two part. That is a plus b is the first language, and then the 0 plus 1 is the second language. So L of a plus b dot L of 0 plus 1. So from this you will be getting a comma b dot 0 comma 1. So here you have to join these two regular expression to a single language. So a0 a1 b0 b1. So finally you will be getting the regular language from the given regular expression. And then this is the closer operator. A star means it is a combination of in all combination of the alphabet A. That is, you can write a power 0, a power 1, a power 2, a power 3, etc. up to a power n. You can write it as. So finally you have to write the language regular expression or equal to, sorry, regular language L of a whole star. That is the regular expression for the given regular language for the regular expression a star. So coming to the next one, a plus b whole star here. So a plus b whole star means any combination of a comma b over the a comma b, any combination of a comma b. So for this you can write L of a plus b whole star, L of a plus b whole stars. So likewise you can write the regular language for the given regular expression 1 plus 0 0 whole star. And then the star operator, here we are using the star operator. So L star, star is nothing but the 0 or more occurrences of the particular symbol over the alphabet. So that is the star operator, 0 or more occurrences. That is the major part here. So if it is plus means which is nothing but the positive closure. Star means star closure. If it is L power plus means which is the positive closure. So positive closure means one or more occurrences of the particular symbol over the alphabet. So here we are using the star operator. Star means 0 or more occurrences. So see here L per star equal to union of I equal to 0 to infinity. L per I. So for that L power 0, L power 1, L power 2, etc. you have to concatenate all the languages over the particular alphabet. So L power 0 means which is nothing but the empty string, so which is null string epsilon. L power 1 and then L power 2, L power 3, etc. which means 0 or more number of concatenations of the particular string over the language. So then coming to the next one. So this is the example, that is the regular expression or equal to a star. So here you have to prove that the L of r star equal to L of r whole star. We have to prove that the given statement L of r equal to L of r whole star. So for this we are taking one example, the regular expression r equal to a part star. So find first you have to find the L of R, language of particular regular expression. So L of R means, so instead of capital R, we are replacing it with A star, which is equivalent to L of A whole star. So finally you will be getting A star. Okay, so here star means what? Which is nothing but the 0 or more occurrences of the particular symbol over the alphabet. So here the symbol A is the symbol. So A part star means 0 or more occurrences of the A, small a. So the first one is you have to write A power 0. So A power 0 which is equivalent to the null string epsilon. And then the second one L power 1 which is equivalent to A power 1, which means you will be getting a single A. L square, that is L power 2 means L dot 2, which means A square equal to A power 1 dot A power 1. So you will be getting AA. So likewise you can combine more number of A's in this. So don't forget star means 0 or more occurrences of the particular symbol over the alphabet. So here the given alphabet is small a. Small a power star means you have to write a power 0, comma a power 1, comma a power 2, comma a power 3, etc. up to a power infinity you can write. So a power 0 means which is nothing but the null string epsilon. If it is a power 1 means you will be getting single a. If it is a power 2 means you will be getting a. If it is 3 means you will be getting a. If it is 4 means you will be getting 4 continuous a's, etc. So finally you have to perform the union on all the languages, that is L power 0, L power 1 union, L power 2 union, L power 3, etc. You have to perform the union operation on all the languages. So this is the closure operator. And then this is the second example of our closure operator, that is R equal to 1 plus 0 whole star. So first you have to write the language for the given regular expression. So here language means capital L, which is used to represent the language. Within braces, within parentheses, you have to mention capital R. R is nothing but the regular expression. So L of R is the regular languages. So here instead of R, we are using 1 plus 0 whole star. So this is equivalent to L of 1 plus 0 whole star. Okay, finally you will be getting within the braces you have to write 1 comma 0 whole star. Here you need to find L star. So first you have to write L power 0. L power 0 means 0 occurrences of the particular symbol. So here we have two different symbols plus 0 and 1. Okay, so here the alphabet is 0 and 1. So L power 0 means 1 comma 0 whole star. So 1 comma 0, here you will be getting 1 comma 0 whole star per 0 means which is nothing but the null string epsilon. And then the second one, L power 1 means 1 comma 0 power 1. This is equivalent to 1 comma 0 itself. So if it is 2 means you have to write it 2 times. So finally you have to combine all the things, that is 1 1 and then 1 0 0 0 0 1 0 0 0 0. So finally you will be getting 4 strings while performing the concatenation operator on the language. And then next one, L power 3 means L power 2 dot L power 1. So in previous step, you will be getting the value for L power 2 dot. Again, you have to concatenate the value of L power 1. So finally, you will be getting the string. So likewise, you have to perform the concatenation operator. Finally, you have to use the union operator to join all the strings into a single language. So at last, you will be getting the regular language. So and then this is the third example for the closure property. So closure means what? It is a 0 or more occurrences. That is, you should keep it in your mind. That is, closure means 0 or more occurrences. 0 or more occurrences means first you have to put 0 and then 1 and then 2, etc. So here the given regular expression is a plus b whole star. So that the alphabet is a comma b here, and then the regular expression is a plus b whole star, and then the language of the particular regular expression r equal to, that is L of r equal to L of a plus b whole star. This is equivalent to a comma b whole star. So first you have to set the value 0, that is L power 0, that is 0th occurrences of the particular symbol. So 0th occurrences means we know that the value is epsilon. Epsilon is nothing but the null string. Okay, so in second step you have to apply the value 1 here, that is L power 1. L is the language, so language power 1. Here the regular expression is a comma 1 power 1. This is equal to a comma b. And then the next one, L power 2 means you have to perform the concatenation operator, that is L dot L. This is equivalent to L power 2. So here a comma b power 1 dot a comma b power 1. So in previous step, no, you will be having the value of a L power 1, no, that is a comma b comma dot a comma b. Finally, you have to perform the concatenation operator, that is from the first set you will be taking a, and then second set like a, and then the next string, no, from first one we will be taking small a, and then second one small b. Like this, you have to perform the concatenation operator. And then coming to the next one, L power 3, which is the concatenation of L power 2 dot L power 1. This is equivalent to AA, AB, BA, BB dot A dot B. Again, you have to perform the concatenation of L power 2 dot L power 1. So finally, you will be getting the result. So that While defining the language, no, you need to combine all the languages into a single language, which is nothing but the L star, L part star, which means L par 0 union, performing the union operation, L par 1 union, L par 2 union, etc. up to you have to perform the union operation on the language. Okay, so here instead of L par 0, you will be getting epsilon. Instead of L par 1, you will be getting A comma B. L par 2, you will be getting AA, AB, BA, BB, etc. So finally, you will be getting the result, that is L star. So this is the language for the given regular expression R equal to A plus B whole star. So here are the examples of the closure operator, that is R equal to A plus B whole star. So likewise we have R equal to 0 plus 1 whole star, and then you need to find the regular language. L is nothing but the language. So from the regular expression you have to form the regular language here, and then the next third one, the given regular expression R equal to AB plus 0 1 whole star. And then here for the given language, in previous one you are forming the language from the expression. So here you are going to construct the regular expression from the given language. Okay, so let's see the first example. So in first example, the language L equal to A power n, where n is greater than or equal to 0. Okay, so here small a is nothing but the alphabet. Small a alphabet means what? Alphabet means it is any symbol from A to Z, or any special character, or it may be a number from 0 to 9, etc. This is the alphabet. The alphabet is the basic building block of this regular expression. Okay, so from the alphabet only you can form the string. So after forming the string, you will be getting the language. So in this particular example, you are going to construct the regular expression from the given language. So the language L equal to A power n, where n is greater than or equal to 1. So first you have to replace the value of n with 0. So A power 0. So we know that the zeroth occurrences of the particular symbol means this is equivalent to the null string epsilon. So see the third column, no, L equal to the first symbol is the epsilon, and then second one you have to apply the value 1, n equal to 1. So A power 1 means you will be getting A power 2 means you will be getting A power 3 means AAA, etc. So this is the collection of strings. So from this you can recognize the regular expression. So we have three different operators in our regular expression. That is, the first one is the union operator. That is, plus is used to represent the union operation. And then second one is the dot operator for concatenation. And then third one is the star operator. So star operator for closure. So closure means what? Zero or more occurrences of the particular input symbol over the alphabet. So here 0 or more occurrences you will be getting. The first one epsilon is the 0th occurrences of the particular string, and then second one small a is the 1th occurrences, second occurrences, third occurrences, etc. So that the regular expression for the given language is A power star. And then coming to the second one, L equal to A power n, where n is greater than or equal to 1. So here in previous one, the value of n is greater than or equal to 0. So here the value of n is greater than or equal to 1, which means one or more occurrences of the particular symbol over the alphabet. So here the symbol, which is nothing but the small a, okay, and then one or more occurrences means, so the initial value of n should be 1. So in previous example, the initial value of n is 0. So here the initial value of n is 1. So the first string for this given language is, it should be A power 1, A power 2, A power 3, etc. A power n. Okay. So if it is A power 1 means you will be getting a single A, which is the first string of the given language. And then second one, while n equal to 0 means you will be getting AA. If it is 3 means AAA, etc. So finally, you will be getting the regular expression A power plus. So we don't have the plus operator, A power plus operator in regular expression. So for that, you need to concatenate a star dot a. Otherwise, a dot a star, this is equivalent to the given regular language. And then the third example, so a power n, b power m, where n is greater than or equal to 0, m is greater than or equal to 0. So we know that if it is greater than or equal to 0 means the first string it should be epsilon, which is nothing but the null string. Okay, so here there is no other conditions uh, for the variables n comma m here. So you apply any value to n and m also, but it should be initial value should be 0. So initial value should be 0 means the first string is epsilon. So first I am applying the value 1 for the string a power n. So here a power 1 means you will be getting a single a, and then b power 0 means epsilon. So we know that the concatenation of any string with epsilon, you will be getting the same string as the output. Okay, so likewise you can apply the n and m value here. So finally you will be getting the regular expression a star b star, a star dot b star. So in fourth example, the given language L equal to a power n, b power m, where n is greater than or equal to 1 and m is greater than or equal to 1. So here the one or more occurrences. In previous third one, no, it is 0 or more occurrences means you have to use star operator, that is closure operator. So here one or more occurrences means you have to use a dot a star into b dot b star. And then next one, so this is building the regular expression from the given language over the alphabet 0, comma 1. So here the alphabet is 0, comma 1. So the given language. So see the first one, the language L equal to W. W is nothing but the set of strings. So W is used to represent the set of strings over the language. So here the condition on W is the W, it should be an odd number of ones. Okay, so this particular language, it doesn't contain any zero, only we have ones, which means odd number of ones alone. So we know that the odd number of ones, so you have to form the string. The first string it should be 1, and then the second string 1 1 1, and then the next one 1 1 1 1 1, that is 5 continuous ones, and then next string it should be 7 continuous ones, 9 continuous ones, etc. So it should be a odd number of ones. So finally, you will be getting 1 1 whole star dot 1 as the output. And then the second example, the same thing, but instead of odd number, here you have to form the regular expression for even number of ones. So even number of ones means the first one, that is 0, that is 1 power 0, 1 power 2, 1 power 4, 1 power 7, etc. 1 power 6, 1 power 8, etc. That is even number of ones. So 0 is the even number, no? So you have to use the first string 0, that is 1 power 0. This is equivalent to epsilon, that is the first string of the given language. And then second one, we are applying the value 2 because 2 is the even number. So you will be getting 1 1. And then the next one, we are applying the value 4. So 4 means 4 continuous ones, and then next to even number is 6. So you have to apply 1 per 6, which is equivalent to 6 continuous ones, etc. So finally you will be getting the regular expression 1 1 per whole star. So these are all the examples. So same thing. First one, L equal to W. W is nothing but the string where the length of W is even. Okay, wow. So here the alphabet is 0, comma 1. So in previous example, we are using the unary representation. So in this, we are using the binary representation. So see here, this is the unary representation. That is odd number of ones alone and then even number of ones alone. So in this, no, here we are using the combination of zeros and ones. In our any string, it is the combination of zeros and ones. So you have to calculate the length. That is the length, it should be even. The first language, no, the length it should be a even. Okay, so even means first you have to put 0, any string per 0, that 0 is the even number. So anything per 0 which is equivalent to epsilon. And then in next step now I'm applying the value 2 for the symbol 0, that is 0 power 2, which is equivalent to 0 0. And then 1 power 2 now I'm getting the even length alone, that is 1 1. And then next one 1 0, etc. Like that we can apply the n value here, but you have to apply the even number of values 0 2 4 6 8, etc. You have to apply the even numbers alone. So finally you will be getting the regular expression 0 plus 1 0 plus 1 whole star, because it should be a even number, no? So you have to choose the first symbol from the first set and then the second symbol from the second set. That is from 0 plus 1 I am taking the value 0. In second 0 plus 1 I am taking the second 0. Finally I will be getting 0 0 whole star. So first, instead of star I am applying 0, means I will be getting 0 epsilon. Instead of star I am applying 2, means I will be getting 0 0, etc. So finally this is the regular expression, that is 0 plus 1 into 0 plus 1 whole star. So same thing here, odd number. Odd number means you should not include epsilon. So you have to start with 1. That is the length of the particular string is starts with 1. So instead of star, I am replacing 1, 3, 5, etc. Likewise, I have to replace. Finally, I will be getting the regular expression 0 plus 1, 0 plus 1 whole star, 0 plus 1 alone. And then the next one, notations of regular languages. So here we are having different kinds of representation, different kind of representation for our regular languages. So regular language means it is a collection of regular expression. So we know the regular expression. So here we have different kind of representations. The first one is the regular expression. RE is nothing but the regular expression. So from the regular expression I can construct the finite automata, which is AENFA, that is non-deterministic finite automata with epsilon transition. From regular expression, I can construct epsilon NFA. From epsilon NFA, I can convert it into the DFA, that is DFA is the deterministic finite automata. From DFA, I can construct NFA, non-deterministic finite automata without epsilon transition here. From NFA to DFA, so finally, from DFA to regular expression, I can construct the regular expression from the deterministic finite automata also. So these are all the different representations of our regular languages. So we have 4 different representations. First one is the regular expression representation, which is nothing but the mathematical or algebraic representation. And then here we are having 3 different graphical representation, that is deterministic finite automata, and then non-deterministic finite automata, and then non-deterministic finite automata with E transition. These 3 are the graphical representation, and then regular expression is the mathematical representation of our regular languages. So here we can construct the ENFA. ENFA means non-deterministic finite automata with epsilon transition. Epsilon is nothing but the null string. So in this we are going to convert the given regular expression into ENFA. So we have the theorem, that is every language defined by the regular expression is also defined by a finite automata. So this is the given theorem. So for this we have 3 different representations. The first one, so see the first regular expression. So the first regular expression is epsilon. For this I can construct the finite automata here. So which have 2 different states, that is the first state and then the second state. So from first state to second state, I can draw one edge with the input symbol epsilon, because my regular expression r equal to epsilon here. Okay, so epsilon is nothing but the null string, which the null string means without reading any input, I can change the state from one to another. So I can change the state from start state to the end state without reading any valid input here. So null string, and then next one phi. Phi is nothing but the null set or null language, which is different from the null string. Okay, which means there is no path from one state to the another state. This is equivalent to the equivalent graphical representation of the regular expression r equal to phi. So first one is the null string, and then second one is the null language, and then third one is the regular expression or equal to small a. So small a is nothing but the input symbol. So this is the valid input symbol, no? So we can change the state from one to another with the input symbol small a. So in edges, no, we have to write the particular input symbol. So while reading this particular input symbol from the current state, you can change the state. So here double circle, which is used to represent the final state. One arrow followed by circle means which is the start state, and then the double circle, which means it is the final state of the graphical model, our finite automata. So here graphical model means which is nothing but the finite automata. Okay, so the first one is the null string, second one is the null set, and then third one is the input symbol. So now coming to the next one, so we have union and then concatenation and then closure operators, no, in regular expression. For that you have three different representations in our finite automata also. So union means what? Either we can move this way or this way. That is the union operator. Okay. So either you can reach the final state through the regular expression, or otherwise you can reach the final state with the regular expression. Yes. So for that you have to draw the finite automata here. The first one r plus s. So arrow followed by small circle, which means the start state. Okay, and then we have the r expression here. Either r also you can reach the final state, otherwise either through s also you can reach the final state. So this is the that is plus operator. Plus means, don't forget, which means the union operation on the languages, union operation on the regular languages. And then coming to the second one, concatenation. Concatenation means continuously you have to combine all the strings over the regular expression or and s. So for this, first you have to draw the finite automata for capital R, and then followed by the finite automata for the regular expression capital S. Okay, and then coming to the star, R per star means closure property. That is closure operator on the regular language. Closure operator means you have to first you have to draw the finite automata for our regular language, regular expression R alone. That is the innermost part alone you have to draw. That is the second state, and then the third state with the input symbol R. Okay, so what is star? Which means zero or more occurrences. So zero occurrences means which is equivalent to epsilon, that is null string. While reading the null string also you have to reach the final state, because null string also the valid string of the regular expression R star. So for that, I have to draw one edge directly from initial state to final state with the input symbol epsilon, because epsilon is the first string. Epsilon is the first string of the given regular language L of R star. Okay. So for this, I have to draw one direct edge from initial state to final state. Okay, so and then I can read n number of times. That is first one a for r power 0, r power 1, r power 2, r power 3, etc. Up to I have to read r power infinity. Okay, so for that I have to form one reverse edge from innermost part. I have to draw one reverse edge with the epsilon transition. So through this reverse edge, no, I can read n number of times the same input symbol. This is r star. So see here, the regular in first example, you have to construct the regular expression. Sorry, we have to construct the epsilon NFA. ENFA means non-deterministic finite automata with epsilon transition from the given regular expression. So here the regular expression R equal to A plus B. So here plus is nothing but the union operation on the regular expression, regular languages. Okay, ma'am. In first step, no, you have to divide this into two parts. So the given regular expression is divided into two parts, that is A and then B. First you have to draw the finite automata for A alone. So we know that you have to draw the state, okay, two state with one edge with the input symbol A. Okay, this is the finite automata for A alone. So and then next one you have to draw the FA for B. So same as our A. So finally you have to combine these into a single diagram. So in this, plus is the union operator. Union means either you can go by this way or this way while reaching the final state. Okay, so from initial state to final state you have to reach either by this way or this way. So throw A, I can reach the final state. Otherwise, either B, throw B, I can reach the final state. So this is the ENFA for the regular expression. And then next one, A plus B whole star. So in example 1, no, we already know the construction of finite automata, that is ENFA from the given regular expression A plus B. So here you have to include star alone. So star means 0 or more occurrences. So we know that the first string of the star operator, no, which is nothing but the epsilon. So while reading the epsilon also, I have to reach the final state from the initial state. You have to draw the edge directly from initial to final state with the input symbol epsilon. And then star means I can read n number of times the same input symbol. Okay, so for that I have to draw one reverse edge. Okay, so through this reverse edge, no, I can read n number of times with the same input symbol. So this is the final diagram for A plus B whole star. So likewise, you can draw the finite automata for any given regular expression. Okay, and then now coming to the properties of the regular expression. The first property is commutative, that is R plus S, which is equivalent to S plus R. Okay, and then the second one is the associative, that is R plus S plus T equal to R plus S plus T. And then the second associative law is Rs dot T equal to R dot St. Okay, this is the associative law. And then the third one, identity, that is R plus phi equal to R. Phi plus R equal to R. So this is identity. Likewise, epsilon dot R equal to R dot epsilon equal to R. Okay. And then coming to the next one, distributive, R of S plus T equal to Rs plus RT, R plus S of T equal to R plus RT plus ST. And then the next one, R plus R equal to R. And then the last one, R star whole star, which is equivalent to star, phi star equal to epsilon, epsilon star equal to epsilon, R star equal to R star, and then R equal to epsilon plus R. So these are all the basic properties of our regular expression. And then, so this is the important lemma in our regular languages. So here, pumping lemma, which is used to prove some languages are not regular. Okay, so this is the theorem which is used to prove that the certain languages are not regular. But using this lemma, no, we cannot prove that the given language is regular. This is only for proving the given languages is not regular, but vice versa is not possible here. So the given theorem, let L be the regular language, then there exists a constant n such that for every string w in L, at the length of the w it is greater than or equal to epsilon, we can break the given string into three different parts. So here w is nothing but the string. So first you have to break this into three different parts. Okay. So while dividing, no, you have to satisfy the following conditions. While dividing the given string into three different parts, no. So for dividing purpose, we have to follow these rules. The first one, that is the length of the y, it should be greater than 0. Okay, so what is y here? The intermediate part, the middle part of the given string, no, it should not be a null string. Okay, it should be greater than 0. And then the second condition is the length of x dot y, which is less than or equal to n. So here n is nothing but the pumping length or the length of the string. Okay, so the modulo xy means the length of xy part. Xy is nothing but the first two part of the given string. It should be less than or equal to n. Okay, So after dividing this into a three different parts, you are going to pump the innermost part, pump the middle part of the given string alone. So pumping means concatenation, n number of concatenation of the particular input symbol. That is, you are going to pump the innermost part alone. So the here, why is the innermost part? You are going to pump that particular string alone. Okay, so the basic application here, see here, pumping lemma is to be applied to show that certain languages are not regular. It should never be used to show a language is regular. That is, as I told, no, vice versa is not possible. This lemma is used to prove that certain languages are not regular. So see here, if L is regular, it satisfies pumping lemma. If L does not satisfy pumping lemma, it is non-regular. So here, these are the examples of the non-regular languages. The first one, no, a power n, b power n, where n is greater than or equal to 1. So using our pumping lemma, we have to prove this language is not a regular language. Okay, so what is pumping lemma? First, we have to take one sample string. So sample string means first you have to apply the value of n. So here we are taking the value of n equal to 2. N equal to 2 means you will be getting 2 a's followed by 2 b's. Okay, that is the sample string. So this particular sample string is divided into three different parts. So for this division, no, you have to follow the rule. That is the middle portion, no, it should be less than, it should be greater than 0. It should not be a null string. Okay, and then the second one, the length of this first first two portions of the string, no, it should be less than or equal to n. So here what is n value? N value equal to 2. We are taking n value equal to 2. So n value equal to 2, no, first you have to take x, divide this into two part, x comma y. So first two symbols, that is a, it should be xy, and then the next of, no, that is bb, it is z. So after dividing this into a three different parts, no, you are going to pump the innermost part alone. So which is the innermost part? The second A is the innermost part, which is nothing but the Y value. You are going to apply the pumping value. So here you have to assign some value to P. What is P? P is nothing but the pumping length. So here I am assigning the value P equal to 2. Again I am applying 2 also. So x value 1a, and then y value, after applying the pumping length, no, I'll be getting a, and then b value bb alone. So finally the result is 3 continuous a's followed by 2 b's. Okay, which means a power 3 b power 2. Okay, but the given language is this, the n number of a's followed by the same n number of b's. Okay, so for this, no, we cannot construct the regular expression and then the finite automata. So if we can construct the regular expression for the given language, no, then the language is a regular language. Okay, and then coming to the next example, so same thing, a power n, b power m, a power n, b power n. So for this also we cannot construct the regular expression, or we cannot draw the finite automata, so that the given language is the not regular languages. And then the last one, L equal to a power n, b power n, c power n, where n is greater than or equal to 1. This is also a not regular action. So what about the solution of this, of these type of languages? We have a context-free language representation. Okay, so in next session, no, we will be discuss about the context-free languages and the context-free grammar, and then its equivalent graphical representation, push-down automata, etc. So in this, no, why we cannot construct the regular languages, regular expression for this, no? So here we should remember the n value. So then only you can read the same number of bits, right? So, but he in finite automata, no, there is no memory unit. We cannot remember anything. Okay. So based on the current state and then the current input symbol only, we can decide the next state. we cannot remember anything here because we don't have any memory unit in finite automata. But the given language L equal to A power n, B power n means here you need to remember the n value. So then only we can check whether the number of B's and the number of A's are equal or not. Okay, so we should remember some value here. So there is no memory unit in finite automata, no? So we cannot construct the finite automata. Okay, so we know that the finite automata is equivalent to our regular expression. So if we cannot construct the regular finite automata means we cannot write the regular expression also. So that the given language, this particular language is a not regular languages. Okay, and then we will discuss some gate questions. Some sample gate questions here. The first question is, which of the following language is generated by the given grammar? So the grammar S tends to AS, BS, epsilon here. So capital S is nothing but the non-terminal. Small a, small b, epsilon are the terminal symbols. So here we have to derive the language. So instead of capital S, I am replacing it with BS. So finally I will be getting AB and then epsilon. Okay. So after that, instead of S, I can replace it with AS. So I'll be getting A, B, A, etc. And then that is finally I'll be getting any combination of A, comma B. So any combination of A, comma B means we have the regular expression A plus B, A whole star. Okay. So A plus B whole star, this is equivalent to the regular language A, comma B whole star. Therefore, D is the answer here. And then the next one. So here, which one of the following regular expression represent the set of binary strings with an odd number of ones? Okay, so here C is the value. That is odd number of ones. There is no condition for zeros, no. That is we have to apply the condition on ones alone, which should be an odd number of ones. So finally, you will be getting 0 star, 1 0 4 star, 1 0 star, etc. So and then the next one. For the alphabet A, comma B, let us consider the regular language. So this is the given regular language. Which one of the following can be a pumping length? So we have the explanation here. We have the explanation here. That is according to the pumping lemma for the regular language, every string W present in the infinite regular language L should be divided into 3 parts X, Y, Z. So we have the condition, no? The length of the inner part, it should be greater than 0. That is, it should not be a null value. And then the length of first two, no? It should be less than or equal to n. So for according to this condition, the value of pumping length, it should be 24. So this is the given answer. So in next session, no, we'll be discuss about more question and answers, and then we'll be discuss about the context-free grammars and the context-free language, etc. So thank you for listening. Thank you very much.